Hello, I am Ryan, and I'm going to be going over the slideshow for our machine learning final project, predicting tech jobs demand in Canada. So, as students entering the tech industry, predicting the tech job demand matters to us because it helps us understand the directions of the job market. In this project, we will explore how machine learning can help us achieve that through neural networks. Our learning problem will be to predict the demand for tech jobs in Canada next year. So the problem is the tech sector, at least in Canada, has seen massive spikes of employment and layoffs over the past decade. Using a data set of Canada's tech sector employment from 2015 to 2025 will be fed to a machine learning model to try and predict the upcoming 2026 job market in the tech industry. The data set we use comes from Statistics Canada and was released on November 27, 2025. As such, given how recently it was released and its source being from the Canadian government, we feel this is a reliable source of data. The dataset uses symbols to define its data quality and accuracy. The legend for it is seen here on the right. Our model. So our model starts with data loading. The file starts with imports of pandas, numpy, pytorch, and torch.nn. We then read the target CSV file, which contains our dataset. It parses through and gathers the job vacancy rate. The data is then cleaned, converting raw strings to numeric values, handling non-numeric values as missing values, then using linear interpolation to fill in the missing values, ensuring a complete series. This is how the graph looks for that data. PyTorch data and the data loader. The data frame is then made with pandas. The job vacancy rate values are then scaled with min-max scaler to a range between 0 and 1. This works to normalize the data, making it easier to train on later. The create sequence function then transforms the normalized data into a sequence, using the past 12 months to predict the next 12 months. Job vacancy dataset is then defined to prepare the data into a format more suitable for PyTorch, then uses the data loader to feed batches of data to the model. Model architecture. The LSTM forecaster class defines the long short-term memory neural network model we use, including the layers. A small test run is performed with an instance of the class with a sample batch of data from the train loader to ensure the model works correctly. Evaluate model on test set. We then evaluate the performance of our trained LSTM model on the data loader data. We switch to evaluation mode, then iterate through the test loader to collect the predictions. Since the model was trained on data that is normalized, the predictions are inverse transformed back to their original state. Then we calculate the mean absolute error and root mean squared error before finally printing the two errors. And this is what the graph looks like on test data. Next, we have the training loop. The training of the LSTM model begins with the NNMSE loss, which calculates the mean squared error between what the model predicts and the actual target values. OPTIM.atom is then used as an optimizer, adjusting the model's weight to minimize the losses. We run through the dataset 100 times with the ENOC value, put the model on training mode, then iterate through the data. We use forward pass, loss calculation, then backwards pass with optimization at the end. We print the loss every 10 ENOCs to see the progress of the model as it improves, which we can see here on the right, as the loss progressively gets smaller and smaller. Forecast. We use forecasting to predict the future. First, we switch to evaluation mode, then initialize current sequence with the range of our previous data, that being 12 months. We then iterate through, feeding current sequence to the model to predict the future. The predicted value, which is normalized, is added to the predictions list. The current sequence is then updated, removing the oldest and adding the newest, resulting in a sliding window effect. Visualizing the data. We finally visualize the data in a graph. We first convert our normalized prediction values to their original state, making them easier to understand. Then we generate future dates and a new data frame to hold our predictions alongside their respective dates. Matplotlib is then used to graph the data and the values we predict from the model. This is what the data looks like just in pure data form. And then this is what the graph looks like. So we can see the blue lines is the historical data that we calculated from a data set, and the red dotted lines is what we estimate it to be.
Alright, in this part of the video, we'll be going over the actual project itself. So I'll cover all these different sections in the notebook, and then I'll show a demo of the training, evaluation, and the forecasting of the model. So I'll start with showing the actual data frame itself. So we load the data set using pandas into a data frame, and you can see this is what the initial data frame looks like. So there's a lot of missing values and a lot of rows of variables that we don't actually use. The main variable that we do use is job vacancy rate. So in the pre-processing and cleaning section, we'll actually extract that row right here. We'll get the values, and then we'll actually format all those values and clean them up. And then for any missing values, so mainly in this data set, the missing values were during COVID-19. So we use linear interpolation to fill those in. And then this is the data set that the model actually trains on. And then we can do some data analysis here, just a quick simple plot of the data so we can see the relationship easier. So we can see that continuously the vacancy rates have been increasing over the years. And after COVID, there's been a big spike, and you can see lasting from 2021 all the way to 2023, the vacancy rates were at an all-time high, and then they normalized into 2025. So this is pretty much the core of the project. This is where we build our LSTM neural network. So this is the long short-term memory neural network. This is what we use for sequential data. So in this case, it was the most appropriate one. And before we actually build it, we have to scale our data. So since activation functions will take inputs of the data values between 0 and 1, we have to scale it using a min-max scaler from scikit-learn. So we can do that right here. And then it gives us an array of all the scaled values. And then we can use that array to create sequences, and then we wrap everything in a data set and data loader. This just allows for batch training. And then we split our data set into training and testing. So we have to split it because we want the model to test on a part of the data that it hasn't seen before. So we do that right here. And then this is the architecture of the model itself. So this is the whole LSTM architecture that we made. So we have two layers here. We have one LSTM layer. This is pretty much going to be computing the outputs, like the patterns, and then it'll be feeding all those patterns into the fully connected linear layer. This layer will be producing the final output using the hidden state, and it will be producing a single prediction. Here we initialize our cell and our hidden states in the forward pass, and then over here we just make an instance of the model just to test it, and you can see the input and output shape of it right here. Now I'll be jumping into the demo itself. So I'll start with the training loop for the model. So the training loop, it will use the MSE loss and the Atom optimizer, which will be updating the parameters. And then for the epochs, we use the 100 epochs to train it here. And then this is the loop itself. So on each epoch, it will be computing the loss. So we'll be comparing the expected and the predicted values. And then it'll also be printing for every 10 epochs. So I'll run it right here and see what that looks like. So you can see the model's training right here, and for every 10 epochs, it's printing the loss as expected. And now that our model has trained, we can actually evaluate it on the test set. So that's the part of the data set that we split earlier, the data that the model has not seen yet. So this is the code for the evaluation. It's pretty simple. We're just going to quickly run it and see how that looks like. So you can see once we evaluate it, it will print the mean absolute error, and it will also print the root mean squared error. And we can use the mean absolute error to actually estimate the model's accuracy. Because these two values right here will tell us how good the model is, or how close the values are to the actual values. So we can use that to predict the accuracy, which I'll run as well. And we get an accuracy of 96%, which is pretty good. And then we can visualize all these predictions using a plot, and you can see the dotted line is the predictions of the model, and then the blue line is the actual test data itself. And then for forecasting, this is where the model is pretty much going to generate predictions for future months using previous months. So we set the steps, the number of months that we wanted to forecast over here, set it to evaluation mode, and then this is the loop right here for forecasting. And we'll run this as well. So now forecasting has been completed, which means we can visualize what the model predicted for 2026 and get our final answer. So we can see this is the data itself from the data set, and then this dotted line is what it's actually predicting. So it continues the graph into 2026 with its predictions, and that's the forecast. And that's pretty much it for the demo.